Liquid helium is an essential tool for cutting-edge research and high-tech applications, including NMR, but handling it isn't as simple as a typical cryogenic liquid. Its extreme properties introduce challenges, particularly when transferring between dewars. Unlike nitrogen, helium gas density at its boiling point affects how much liquid is actually moved. Let's explore why.
At 4.2 Kelvin, helium behaves as a normal liquid, yet its distinct characteristics complicate handling. Low density. Liquid helium has a density of 0.125 grams per milliliter, much lower than nitrogen. Rapid expansion. Helium vaporizes easily due to its very low latent heat of vaporization, 20.4 kilojoules per kilogram. Gas density matters. At boiling point, helium gas has a density of 0.016 grams per milliliter, which is relevant when accounting for the amount transferred. Compressibility effects. Unlike nitrogen, helium's high compressibility means its volume changes noticeably with small temperature fluctuations. To accurately track transferred helium, we must account for both liquid and gas displacement during the process. Cooling helium from room temperature to 4.2 Kelvin requires cryogenic refrigeration, relying on techniques such as Joule-Thomson expansion or gas compression. The key energy values are that cooling energy demand is several thousand kilojoules per kilogram just to get the gas cold, and then the latent heat of liquefaction is much lower, only 20.4 kilojoules per kilogram. Far lower than the latent heat of liquefaction of nitrogen, which is 199 kilojoules per kilogram. This means that helium requires extensive refrigeration, but relatively little energy for the actual phase change. When transferring liquid helium, we must consider both gas displacement and boil-off losses. The best practices for transfer efficiency are 1. Displacement awareness. The receiving dewar contains helium gas which must be accounted for when calculating liquid fill. 2. To minimize boil-off. A warm dewar accelerates helium vaporization, reducing the amount that remains as liquid. 3. Pre-cooling dewars. Cooling the receiving dewar before transfer reduces immediate losses. 4. Tracking mass instead of volume. Since helium gas contributes significantly to volume measurements, tracking the mass difference between dewars gives a more reliable estimate. These methods help laboratories minimize helium waste and ensure accurate transfer estimates.
I'm here in cryogenics. We're going to start cooling down this helium dewar from room temperature, and then we'll fill it with helium. So first we fill it with liquid nitrogen, or put liquid nitrogen in to cool it down. Let's go for it. Now have it full of nitrogen. So now you're just going to take out the pipe and leave it till tomorrow, right? Yeah. The dewar has had liquid nitrogen in overnight, and now we're going to siphon off the liquid nitrogen and then cool down for helium. So this is going to be sent to the dewars on the side. In order to push the nitrogen out, we have to connect some pressure from the side here, and this is helium gas, and that way, as we push the nitrogen out, the nitrogen gas inside is exchanged with helium. Once it's completely empty, then we can continue. Now we have completely filled it with helium gas and emptied it of nitrogen liquid. So in a few minutes we're going to start transferring helium. So now we put in the helium transfer line. This is the line for helium recycling. Now, opening, we start to transfer helium. Okay, in the meantime, the helium is liquefying, the mass is going up, and you can hear in the background the compressor recycling the helium for further use as it evaporates off. There's already liquid helium forming inside and returning it to recycling. Since it was going very slowly, we added a little pressure by putting the heater on. So now we're closing off. We reached the requested weight. Okay. So when can it be moved? Ah. Okay, that will take a while. Yeah. So we have to wait till it defrosts and then it can be moved.
have seen the complex process of filling a helium dewar, so why does nitrogen not face this challenge? The key lies in density and vaporization behavior. The boiling point of liquid helium is 4.2 Kelvin, while that of liquid nitrogen is much higher at 77 Kelvin. The liquid density of helium is only 0.125 grams per milliliter, while that of liquid nitrogen is much denser at 0.807 grams per milliliter. The gas density at helium's boiling point is 0.016 grams per milliliter, which is more than a tenth of its liquid density. That is why you have to take the gas into account. On the other hand, in the case of liquid nitrogen, the gas density at its boiling point is 0.0046 grams per milliliter, which is much less than 1% of the liquid density. The boil-off impact of liquid helium is much higher than that of liquid nitrogen. Why nitrogen behaves differently? Higher liquid density means volume estimates are reliable. Lower gas expansion effects make displacement negligible. The higher latent heat of vaporization slows down boil-off. Helium requires precise handling due to rapid evaporation and its compressible gas phase. To better visualize helium's behavior, we can use carbon dioxide near its critical point just above room temperature. Carbon dioxide enters a supercritical phase, losing distinct liquid-gas separation similar to helium just 1 degree above its boiling point. This demonstrates how helium's behavior near 5.2 Kelvin differs from conventional liquids. When cooling again, the phases separate. Helium recovery is crucial for sustainability. Measuring recycled helium requires correcting for temperature and pressure effects. How to accurately measure recycled helium? 1. Record the amount of gas collected by measuring its pressure in a known volume, typically measured in cubic meters. 2. Correct for temperature changes using the ideal gas law correction that P corrected equals P measured times T standard divided by T measured. 3. In the collection sac, correct for the pressure as well, such as V corrected is V measured times T standard divided by T measured times P measured divided by P standard. This method ensures the optimization of helium reuse and minimizes loss. We now return to the NMR lab where the liquid helium is being transferred to the magnets.
Handling liquid helium efficiently means understanding displacement effects, boil-off losses and accurate measurement corrections, whether for research or industrial use. Following best practices ensures minimal waste. And speaking of advanced research, Hebrew University's NMR facility offers state-of-the-art cryogenic solutions, high-field NMR spectrometers for molecular research, expert support for chemistry, biology and material science, efficient helium recovery systems. Join the Hebrew University's leading-edge spectroscopy community. Contact us today to take your research further.